Okay, hello everyone. It looks like I've got a little bit of switching there, toggling back and forth between my screen and my Visual Studio. Okay, looks like it's stable now. All right, so we're going to be going over the lecture for our graphs and graph algorithms. Just something before we start. The department is looking at the announcement from the provost and the associate dean of engineering for education are talking about grading, and so we're waiting to hear back from the department on exactly what we're going to do about people who are like in the C- range. So I'm waiting to hear from the department what we should be doing there. We're going to do whatever the department says to do that's consistent with what the university wants us to do. But what we will be doing is when grades are assigned, we will be putting them onto Wolverine Access as usual. We put the grades on, and by default, it will show up on your transcript as either P or NRC. What we will also do is we will take our spreadsheet and we'll send everyone an email like we did for the midterm. It says, unable to connect to chat, please try again later. Okay, so it says to me, it says that I'm typing. Can anyone else type something into the chat window so I can see if it's working? I haven't actually done this live before. I just did it testing it with no one there. I haven't actually done this live before. Okay, hello. I just did it testing it with no one there. Yeah, for some reason my screen, I cannot connect to chat, but I changed to a different window and I can see chat. So it's weird. I can see what I type. I can't see what you type unless I switch to an actual live view. Well, as long as things are going okay and you're able to type, I can see it in the as I'm viewing the window as a viewer instead of as a presenter. I haven't actually done this live before. I just did testing it with no one there. Yeah, for some reason my screen, I cannot connect to chat, but I changed to a different window and I can see chat. Yeah, it's just so it's weird. I can see what I type. I can't see what you type unless I switch to an actual live view. Well, as long as things are going okay and you're able to type, I can see it in the tell everyone viewing the window as a viewer instead of as a presenter. I haven't actually done this live before. I just did testing it with no one there. Yeah, for some reason my screen, I cannot connect to chat, but I changed to a different window and I can see chat. Yeah, it's just so it's weird. I can see what I type. I can't see what you type unless I switch to an actual live view. Well, as long as things are going okay and you're able to type, I can see it in the tell everyone viewing the window as a viewer instead of as a presenter. I haven't actually done this live before. I just did testing it with no one there. Yeah, for some reason my screen, I cannot connect to chat, but I changed to a different window and I can see chat. Okay, how about now? Okay, are we down to 1 now that's understandable? Okay, so now it's good. All right, I'm going to have to practice with this a little bit more. We'll make it smoother next time. Like I said, lots of new things for all of us to learn this semester. Okay, so if things are better, let's actually, I'm going to repeat what I said so it's hopefully understandable. So we will be entering grades on Wolverine Access. We will get, oh great, back to the third dimension again. Okay, so is it audible now in a reasonable fashion? Okay, audio is fine. All right, so when we put in the grades at the end of the semester, we'll send out the estimates like we did mid-semester. We'll send an email to everyone. It'll show you what grade you will receive if you choose to uncover your grade. Okay, good. I'm glad things are working now. So we'll get this figured out. What'll happen with those borderline grades of C minus? Once the department tells us what to do about those, we'll enter them in and we'll send you an email like we did at midterms, and then you can choose if you want to uncover your grade or not. For most of you, it's going to be you want to uncover the grade because most of you are going to be passing. All right, so let's go to the lecture for today. So we're going to start talking about graphs and graph algorithms. And we've got an example here of a board game. And the board game is called Ticket to Ride. It's about laying railroad tracks across the country. And there's other games that we'll reference in here. Like on the front page, there's an example of Settlers of Catan. So anyway, another one we're going to use as an example throughout this lecture is this presentation of airline routes. And we're going to use this example over and over and over again. So in this picture, we've got some airports and their 3-letter abbreviations along with their numbers to go from one to another. Those numbers could represent mileage, they could represent dollars, they could represent time. It's just some number associated with it. And if we want to do an exact example, then sure, we're talking about dollars or we're talking about miles. Now, when we've got a graph, we're going to have a formal definition of a graph. So a graph is a set of vertices together with a set of edges, and the edges connect pairs of vertices. So really, the edges can be thought of as a set of tuples, of pairs of vertices. So, is this a graph? This should look familiar to you from last lecture when we were doing the binary tree deletion, or the AVL tree deletion. So is this a graph? Well, it has vertices. It has edges that connect the vertices. Okay, so someone's confused. You are probably seeing this not quite live. Okay, go over that again. I'm not sure which that you're referring to. We've got to be specific here because I'm about probably 20 seconds ahead of you. You're not quite hearing me live, but almost. Okay, well, you've got to be specific about what I need to repeat. the last slide. Okay, so that would be the generalization. So a graph is just this collection of vertices and a collection of edges. So the vertices, we would list out the vertices like A, B, C, or 48, 62. So we will list out what the names of the vertices are, and we'll also, okay, you figured it out. All right, so is this a graph? So this question, is it a graph? Well, it's got vertices, it's got edges that connect vertices. Sure, that meets our definition of a graph. What about if it's not a tree anymore? Now it has cycles, which means it's not a tree, but it still meets the definition of a graph. What about if there were two different ways to get from one vertex to another? That's still a graph. That could represent, say, if this was planes and flying, maybe there are two different airlines that I can take to get from one place to another. What about if there are disconnected regions? Does it still meet our definition of a graph? It still has vertices, it still has edges, and if it meets our definition of a graph, sure, that's a graph. It's a disconnected graph. It has places you can't get to from here. Okay, so in more detail, when we make a graph, we often are going to have these conditions which we might want to disallow. So for instance, I've got parallel edges are allowed in a general graph. Self loops are allowed in a general graph. But if we get rid of those, if we disallow them in a specific circumstance, we can make things a little bit easier on ourselves. So if I get rid of the parallel edges, then we can make things a little bit simpler. And if I get rid of the self loops of a vertex that connects to itself, things get a little bit easier. So unless we say otherwise, we're talking about a simple graph. So is this a simple graph? Well, it is disconnected, which is okay, but we have this self edge where a vertex connects to itself. So this is no longer a simple graph because of that edge. If we take that edge away, we do have a simple graph. It is a disconnected graph. Hector, I'm just going to pause here for a second. I'm going to add something in here. I'm going to just pause here for a second. I'm going to check our settings. And I'm going to add Hector as a moderator of this channel, which I think I may have forgotten to do. Okay, so Hector, you should be marked as a manager now. If that allows you to do anything, we'll see. Sorry that we have people who feel that they have to ruin other people's channels in order to enjoy themselves. Okay, anyway. So is this a simple graph? Well, since we've eliminated the duplicated edge, then we've got a simple graph, even though it's disconnected. So a couple definitions that we're going to need moving forward. A simple path is this sequence of edges that leads from one vertex to another with no vertex appearing twice. So a simple path would be, say, I will take a walk from my house down to my neighbors and drop off something for them, and then I'll get in my car and I'll drive to work. So I've never repeated anything in that path. Now, a connected graph is when we have a simple path between any pair of vertices. So a connected graph says, basically, you can get there from here. You can go from one node to another and get to every other node. If there isn't a simple path between a given pair of vertices, then it's not a connected graph. For whoever's saying they missed the slides, remember, you can rewind, and if you're part of my class, you can go and load the slides from our Canvas webpage. If you're not part of the class, then, I mean, it's not that we don't like to have you here, but the slides are available for my students. Okay, so then in a cycle is when we have a simple path, except the first node and the final node is repeated. So a cycle would be going from, say, A to B to C and back to A. Okay, when you ask me to go back, for my students, when you ask me to go back, I need a point to go back to. Okay, another definition, directed versus undirected graphs. So in a directed graph, edges have a direction. Well, it looks like to my students, I'm going to have to say, we're going to have to find something else other than YouTube Live. I guess we're going to have to go to the Zoom so that we can keep it private in the future. I'm going to try to get through this. Yep, I know, Nick. Nick, I recognize your name. So I'm going to be going through this and ignoring people whose names I don't recognize, which is unfortunately some of you who are real students. So I'll take serious questions seriously. Okay, so directed graphs, edges have a direction. And when edges have a direction, the order that we list the vertices within an edge matter. So when I say I have an edge from U to V, then if I have an edge from U to V, that means that, if I list the edge U comma V, it means I have an edge from U to V. In an undirected graph, it doesn't matter which order we list the vertices within an edge. The edge connects those two vertices, and we can go in either direction. Okay, so we've got an example here. I know this graphic is a little bit hard to see on the screen, so I'm going to add in here just a little bit, darken those arrows that connect in the directed graph, that direction and that direction. Okay, that's a little bit easier to read now. Okay, so we've got our arrows in the directed graph to connect it and to show us which direction we're going in. Just an example of how we'll see a directed graph. Okay, so for Alan, so your question about directed versus paths or cycles, etc., I could have a simple path with or without directed edges. It's just that if there are directed edges, I'm limited which direction I can go. So for example, in the undirected graph here, I could go from 1 to 2 to 4 or from 1 to 4 to 2. In the directed graph, though, I can only go from 1 to 2, and then I can go from 2 to 4, but there is no direct edge going from vertex 1 to vertex 4. So they're sort of independent. we can have a simple path whether we have a directed graph or not. So Alex, your question, if there's only one directed edge, is the whole graph directed? I suppose that would make it so, but if I was going to do that, what I would do is I would show you in the graph, for instance, I would show you this edge between 3 and 4 is bidirectional. So we will tend to either put arrows on every edge or none of the edges. We won't just put it on some of them and make you guess about the others. Okay, is that better, Alec? Okay, I'm slightly delayed again. I'm delayed by or I should say you're delayed. I'm ahead of you by 30 seconds. Okay, so another thing that we could associate with each edge is a weight. And so the weight of an edge is a number associated with it. No matter what I call that number, it's going to give you some connotation about it. So if I say that it's weighted, it might make you think of pounds or kilograms. If I say it's a cost, it'll make you think of dollars. If I say it's a distance, it'll make you think of miles. But really, it depends on the context. What the number means is dependent upon the context. Okay, so we might have these edges on a graph, and then in an undirected graph, the weights could be different if we had parallel edges, if we allow parallel edges. If we have directed edges, we might have a different weight for the different directions. Generally, when we're talking about algorithms that search on a graph, they're generally going to search for either a path in an unweighted graph to say, can I get from here to there? Or if I have a weighted graph, a more common question is, what is our least cost path to get from here to there? Okay, so we've got our graph here from the earlier slide with our plane routes and our numbers. So since there's numbers here on every edge, it must be a weighted graph. Since we don't see any arrows at all, it must be an undirected graph. Now, when we talk about the complexity of a graph, we could give the complexity in terms of the number of edges, the number of vertices, both, or something else. Now, when we write these, since E and V are both sets, it would be more proper to write the vertical bars around E to say the size of the set E. But generally, if you see things like O of E, that means the same thing as O of the size of the set E. So we'll usually stay with the first one just to be a little bit less to write. So for instance, if we look at how many edges are there in a graph? Well, in a complete graph where all possible edges do exist, then the number of edges is equal to V times V minus 1 divided by 2. Now remember, we said if we don't say otherwise, we're talking about a simple graph. So in a simple graph, this is the maximum number of edges is when the graph is completely connected. In a dense graph, we would say a dense graph is a graph where their number of edges is proportional to v squared. And we can represent that as an adjacency matrix. We'll talk about that soon. In a sparse graph, we could say that E is much less than v squared, or that E is proportional to v. There is no hard and fast rule about where is the dividing line between a dense graph and a sparse graph. So it really comes down to when we look at a couple of different algorithms and we look at the different complexities, it would be a call there is this graph, does this graph have a number of edges that would make it more attractive to use the sparse graph representation and the algorithm intended for sparse graphs, or should we go with the dense graph representation? So when we have a sparse graph, we'll represent it as an adjacency list. In a dense graph, we'll represent it as an adjacency matrix. Okay, just a second. I apparently can. I should have been doing this myself. Okay. I'm getting rid of people's messages so that you won't see them. Apparently, I still see them. Oops, sorry. I accidentally hit. So I'm trying to do 3 things at once here. And now I'm waiting for my video to catch up with me. Okay, so it turns out that I can mute people who are abusing our channel. So I'm sorry I wasn't doing that sooner. I don't know, it should be, Hector should have the ability to do that now if he refreshes his screen. He's marked as a manager. Okay, so back to where we were. Okay, sparse graph, dense graph, got it. Okay, so for example here with 5 vertices, we've got our complete graph would have 5 times 4 divided by 2 is 10 edges. Our dense graph has, looks like it's missing 2 possible edges, and our sparse graph has 4 edges. With a graph this small, it really doesn't matter whether I represent it as an adjacency matrix or an adjacency list, or whether I call this sparse or dense. With so few edges. Oh, good. Thank you, Hector. All right. Well, good that we got that taken care of and we've learned from it. Now we're ready to mute people faster when they are not asking relevant questions. You're welcome. All right, so now hopefully it'll be easier for me to see relevant questions. Okay, so in this graph, again, there's no hard and fast rule about where do we draw the line between them. But when the number of edges is close to v squared, definitely dense, close to v, definitely sparse. Now in this graph, well, since there are edges that we could have drawn that we didn't, it can't be complete. Since the number of edges here, yeah, Sam, we might have to try something like that. And I'll see, we might want to keep it semi-private while we're presenting it and then make it public later. So I'll look into that. And what I'll do is I'll do a practice recording. Yep, we'll worry about that later. So anyway, let's get back to our sparse and dense. So this one, definitely not complete because there are edges missing, because I could connect those two vertices with an edge. So it's not complete, and in fact, as this is, if I were to take any edge out, it would be a disconnected graph. So we're at the bare minimum number of edges to have a connected graph. It's got to be sparse. Now, how many edges are there here? Well, if I've got V vertices, the number of edges in this graph is equal to the number of vertices minus 1 is the minimum number of edges to get us a complete, to get us a connected graph. So this one's definitely in the sparse category. Now here is how we could represent this graph as an adjacency matrix. Now, I normally would like to put trues and falses in the table. However, when I filled this table with true and false instead of 1 and 0, it got really hard to read and tell apart. Maybe colors would have worked better, but being colorblind, I usually don't think of that as my first solution to a problem. So I just went to 1s and 0s here. So 1 means there is an edge between those two vertices, 0 means there's not. Now we can see that since this is a simple graph, everything on the diagonal here is all zeros because no vertex is connected to itself. Also, we've got some duplicated entries here, such as, so for instance, LAX SFO, there's a connection in the LAX row, and there's a connection in the SFO row. Now, here's the equivalent distance matrix with putting in the values from the graph into the table. Now, 0 here is not necessarily the best value to put there. With true and false, 0 made more sense. If we treat these integers as Booleans, 0 would be false. But if we try to do something where we're minimizing, 0 wouldn't be the best value to put in here because then 0 would look like the best possible value. Okay, so in the adjacency list, we're going to come back to our representation. In the adjacency list, we've got our connection from, if we look at the SFO row, SFO is connected to LAX and DFW and ORD and BOS. In the adjacency list shown down below, the equivalent list, the order does not matter. The orange box, SFO, think of the SFO as the starting point. From SFO, we can get to anything in that list, but the order of the arrows doesn't show us which order we must follow. So we can go from SFO to anything in that adjacency list. We can go from LAX to anything in its adjacency list. The rest of the adjacency list would have to be, we'd have to have more entries in there. And I didn't have quite room enough to fit it all on one slide. But we can imagine we would have about 5 more lists there. All right, so then in the adjacency list, we could have nodes contain a distance. For example, from SFO to LAX is 337. We could make that box a little bigger and put the numbers in there also. Really, in a data structure, we would make something like a node. The node would contain the other vertex and the weight from the graph. Now, when we look at the adjacency matrix. If we store the entire matrix, it's going to take us V times V space. Alex, the graph would always be symmetric if it's an undirected graph. So if it was a directed graph, then it might not be symmetric. In an undirected graph, it is going to be symmetric. Yes, exactly. So Alex's question, yes, it's symmetric. So for Arjun's question, if our graph was directed, then no, the adjacency matrix wouldn't be symmetric, and neither would the adjacency list. The order doesn't matter because we're just saying we can get there. Yep, all of those are right. Okay, so back to this slide. When we're talking about the matrix, the directed graph would have a to and a from, and which way we go would make a difference. Like we would have to say the row is from and the column is to. So we'd have to make that clear in a directed graph how we represented the adjacency matrix. In an undirected adjacency matrix, we could eliminate about half the space. So if we go back to our graph, our matrix over here, we could essentially eliminate the diagonal because we know it's a simple graph. And we could eliminate everything above the diagonal. Again, this is if it was an undirected graph. We could eliminate a lot of that information. However, then it would make it harder for us to look things up, because then I would have to say, well, you want to go from SFO to ORD, but I can't look that up in the SFO row. I have to look it up in the ORD row. And that would make it more complicated. And we don't like making things more complicated if we don't have to. So it only needs half the space, but really, I wouldn't do that. I would just stick to the whole V squared, make it easy to find things, make it easy to index things for the undirected graph. In an unweighted graph, like we said before, in the unweighted graph, we could just use Boolean, true and false, or 1 and 0. In a weighted graph, a better representation would be infinity for the ones that don't have a connection. Now, if we look at how we can do that, so in the table representation, that's easy. I just put an infinity symbol there. But what we need is a way to do it in code. So when we do it in code, what we're going to do is include the library called limits. When we include limits, we get something called numeric underscore limits, which is templated, and then numeric underscore limits of type name, : infinity, is a representation of infinity. Now, not every type has infinity. There's another thing called numeric limits of type : has infinity, which will tell you true or false. Basically, float and double are the only ones that have a real representation of infinity. If you ask an integer type, like numeric limits of int infinity, it'll give you the same thing as numeric limits of int : max, which would be like 4 billion-ish. So numeric limits of double infinity is a little bit better because if we do common things like adding something to infinity, it stays infinity. Subtracting something from infinity, it stays infinity. As long as we're not messing with like infinity and infinity. And I posted in there a little bit of oddities between G++ and Visual Studio, the way they're treated differently. Mostly we're not going to be doing those things. Usually we're going to be adding things up. We're going to add a value to an existing value, and we're going to try to find the smallest one, the smallest total. Okay, so why does 0 not work? The reason 0 doesn't work is it doesn't work if we're adding things up. If we're trying to find the shortest path, 0 is a misleading shortest edge because it looks like no cost. So it would be better to put an infinity there and then, hey, that edge of length infinity, that looks terrible. Let's not pick that one. So it makes it more problematic when we're trying to find the best way. Okay, so when we have double, numeric limits of double max is not as useful as infinity, because if we subtract something with max, it goes down. If we subtract an integer from infinity, or we add an integer to infinity, it doesn't change. Now, in the adjacency list, we're going to assume that there is a random distribution of edges. So if there was a random distribution of edges, meaning it's not all of them go into one vertex, then we would expect there to be approximately E divided by V edges on each vertex list. So let's go back to an example here. So in this graph, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It looks like we've got 13 edges, and we've got around, I think 21 would be the maximum. So we've got about 13 edges out of 21 possible. But if we look at the adjacency lists, I've got just 2 adjacency lists, and I've already got 7 entries. Remember, in an undirected graph, everything's going to be there twice. So that's why we said it's going to be proportional to E divided by V. In an undirected graph, it's really going to be proportional to 2E divided by V, because this SFO LAX, that one number, is going to appear in 2 different adjacency lists. Okay, so we would say that the average list is about size E divided by V. Really, it'd be 2E divided by V if we are in a undirected graph. If I want to access a vertex list, so I'm saying, hey, let's get to the front of the SFO list. We can get to the front of the SFO list in O of 1 time. Wait a minute, how are we going to get there in O of 1 time if it's a word like SFO? We could use a hash table. So even if we have node names that are strings, I could still get to one of those linked lists in O of 1 time if I use a hash table at the highest level. So I can get to one of those lists in O of 1 time, and if I want to say, hey, is this edge in this list? Like, I'm looking at SFO, can I fly directly from SFO to ORD? Well, I can get to the SFO list in O of 1 time, and then I can look through that list in approximately E divided by V time. Some will be a little bit longer, some will be a little bit shorter. If we look at the average cost for an individual vertex, like to say, hey, let's list off everywhere that you can get to starting in San Francisco. It would take us O of 1 to get to the head of the San Francisco list, and approximately E divided by V time to print out everyone within that list. If I wanted to, say, print out everyone in my adjacency list, like list me all the flights that exist right now, which granted, there aren't a lot of them right now, but if we list them, it would take us O of V time. We would have to go through every vertex, O of 1 to get to that vertex's list, and E divided by V time to go through it, which gives us a total of O of V plus E. So if I want to print out everything in my adjacency list, it's O of V time, because I've got to say, hey, here's the San Francisco list, and here's everything in it. Now, the nice thing about the adjacency list representation is the directed versus undirected kind of takes care of itself, because the undirected, everyone will just be there in there twice. In the directed graph, it'll only be in the list if you can go from the start of the list to the one that's listed. Also, in the weighted versus unweighted takes care of itself, because here we don't need a representation for infinity. If it's not in the list, you can't get there. Well, okay, so Arjun, if I have to traverse the list, then a hash table for the list is, remember we said when we talked about hash tables, we don't really want to use a hash table if what we're mostly doing is traversing the list. So a hash table here would be good at the high level to get me to that list, but then going through the list, I would say either make it a linked list or maybe we could make it a vector. If I made it a vector, then it would get rid of the slowness of linked lists. But we really don't need a hash table for one list. We'd be overdoing it there. Okay, I'm reading Elang's question. Doesn't hashing string take O and? Well, Elang, usually when we're talking about strings, we usually, unless we're doing something really strange like DNA analysis, usually strings have an upper limit to their length. Like in this example, all of our airports have a 3-letter code. So we never have to take O of n time. It's really O of the number of characters, which is, with the airports, is an upper limit of 3, which is constant. If we're talking even English words, most words have like 7 characters or less. Very few common words have more than 10. So really, unless we're in a special case where strings do have arbitrarily long length, it's usually safe to say it's O of 1 time. Also imagine if you're the person writing the STL hasher, maybe you took that into account, and as a string gets longer and longer, less and less of the characters get used in the fingerprint, so that maybe we start skipping characters to get the hash to be a more reasonable time. Okay, so O of 1 to access a vertex list, we just went through that. We could hash that out. We could use either a vector or a linked list for the things that we can reach once we get there. So we could have a hash table from strings to linked lists, or a hash table from strings to vectors. Now what we've got here is we've got a couple of questions that we want you to take a couple minutes to answer. So first of all, I've got the adjacency matrix view, the adjacency list view. The goal here is determine, I give you 2 cities, X and Y, and you want to determine if you can get from X to Y directly, one flight, and tell us what would be the worst case complexity, the best case complexity, and the average case complexity for each of those representations. So take a few minutes, think about it. I'm going to start my labels for them, and then if you want to use the chat, you can do that. We'll come back in a few minutes and talk about the answers. It's a little bit harder for me to judge how much time to give you when I don't have people in front of me. I usually judge by the volume level in the room, and it goes up as people are getting into it, and then it starts to go down as they've got more answers worked out. Okay, so let's get back to this. So for the adjacency matrix, let's stick with one representation. We'll do best, worst, average for matrix, and then we'll do best, worst, average for the adjacency list. So I say, hey, can you get from DFW to MIA? Well, I go to the DFW row, I go to the MIA column, I see a value there, that's O of 1. And whether it existed or not, it's O of 1 for all of them. Yep, as someone pointed out. So for the adjacency matrix, it's always O of 1. This is an easy question to answer. Now, what about the adjacency list? Let's say that right now flights are starting to disappear. All right, so in the best case, I say, hey, can I go from SFO to, oh, I got lucky, it's at the head of the list. So it could be best case is O of 1 because there it is, it's at the head of the list. Or it could be best case, and again, best is sort of relative here, it could be best case because I'm looking at the flights leaving SFO and there are none of them. So it doesn't matter where you want to go, you can't get there now because there are no flights. So it could be O of 1 because the list is empty right now. There are no more flights today. Okay, what about the worst then? Well, then the worst case would be it still takes me O of 1 to get to the list, but then I've got to search everybody in the list because maybe the one I'm looking for isn't in there and I have to search the whole list, or maybe the one I'm looking for is the last one in the list. How big could the list be? Well, since we've got unless we say otherwise, we've got a simple graph. Since it's a simple graph, the adjacency list can't be longer than v minus 1, which means O of 1 plus v. So O of 1 to get to the head of the list, v to search the list. Really, it would be we could just say it's O of v. Now for the average case is a little bit more complex. Let's assume that this list is not completely full, like it doesn't have all possible airports in this list. Then it still takes us O of 1, O of 1 to get to the list. It takes us O of 1 to get to the list, but then we've got to traverse the list. The list would be on average about length E divided by V. If the airport we're looking for is in there, it would be E divided by V divided by 2. If it's not in there, it would be just E divided by V because I have to go to the end of the list. But either way, it's going to be about O of E divided by V, about the length of the average list. Okay, next question. We just changed the question a little bit. Question is, what is the closest other airport starting at X? Yes, Sam. So really, it also comes down to dense versus sparse. If this graph was really dense, then the adjacency list would be a little bit more unwieldy. But if it was a sparse graph, then the adjacency list might be more efficient because it would take up less space. Why divide by 2, Rajiv? Why would we divide by 2 is if the city you're looking for is in the list, we would find it on average about halfway through the list. Sometimes it would be the first one, sometimes it would be the last one. On average, it would be halfway through the list. So the length of the average list would be E divided by V, and if it's in there, we would find it about halfway through. But it would never be worse than the length of the list, and in the average case, we assume the length of the list is about E divided by V. Okay, so different question. So different question is, what is the closest other airport starting at X? So I'm somewhere, I want to fly, and I'm not that worried about where I'm going, I just want to get out of here. I want to get to the closest other place that I can, or maybe instead of closest, let's change this to cheapest. and these are dollars now instead of miles. So if these values represent dollars, I want to find the cheapest one I can get to. And we're going to ask you to do the same thing again. For each representation, come up with the best case, worst case, average case complexity for each representation to find the cheapest other airport starting at X. So you can go ahead and work on that. I'll get the categories ready. Okay, so let's look at this problem. All right, so in the best case of the adjacency matrix, I go to the row, that's easy. Once I get to the row, I have to look at every value. So let's say I'm at Dallas-Fort Worth, DFW. I start at DFW, I have to check everything in there. I see 1464, that's the cheapest. Wait, 1235 is cheaper. Infinity is not better. 802 is better. 802 is the best. 1121 is not better. Infinity is not better. Infinity is not better. I had to look through all of them, O of V. Well, if that's the best I can do, it's also the worst I can do, because that's how many I have to look at. So adjacency matrix O of V, you have to look at the whole row. Okay, just a second, let me read that question. Oh yeah. Either matrix row or matrix column, it doesn't matter. Since we're in an undirected graph, it doesn't matter which we use. All right, what about the adjacency list? In the adjacency list, the best case, best in terms of complexity anyway, the best case is I go to the SFO list and it's empty. Work as a priority queue? Well, the problem with the priority queue, Rajiv, is that we don't have a way to iterate through it. I can't iterate through a priority queue without destroying it. I have to pop them off. Okay, so then the question, adjacency list. So the adjacency list, if we knew we were going to be asking the same question over and over, then yeah, then maybe we could order the lists to optimize it for that question. But we're just talking in general. So if I've got an adjacency list and I don't know anything about its ordering, I'm going to have to look through each linked list. So we're talking in general, what can we do? All right, so for the adjacency list, assuming it's not in any particular order, the best complexity would be when I get to the SFO list and there's only one thing in the list, or there's none. If there's none, there's nowhere that's the cheapest airport I can reach. If there's only one thing in there, it's the only one I look at. So the best here could be O of 1 because the list is either empty or has one element in it. The worst would be O of V because I have to look through all V minus 1 vertices in this one. And then the average would be O of E divided by V because I have to look at the average linked list is of length approximately E divided by V. Okay, different question. I want to know, are there any flights that can get me from airport X? So I just want to know, like, I'm just looking at things from home. I'm checking queues and stuff and seeing if there's any flights. I want to find out if there's anywhere that I can go from a particular city before I even get to the airport. So go through and look for the best, worst, and average for each of these. I'll get the headings written up there while you start thinking about it. How would we determine the weights? I drew it once before, and I didn't update all the slides. To get the weights from the vertex list, what we'd have to do is we'd have to add more data to it. Like I'd put a 337 in there and a 1464 in here. We'd have to modify the list to have more than one piece of information at each node. Okay, so for this one, okay, so we're looking for the determine if any flights exist. In the adjacency matrix, I could always get lucky and find it in the first one. Like I start in the LAX row. I say, are there any flights from LAX? Oh, look, the very first column has a value. We could be O of 1 here. And yeah, someone's intuition is right, Rajiv. Okay, so in the worst case, do any flights exist? Well, in the worst case, I start out in a row, let's say like JFK. I start out in the row JFK and I find infinity, infinity, infinity. I could keep getting a bunch of infinities and before I ever find a value. So the worst could be O of V. In the average case for the adjacency, I think JFK is a good example there too. If there are values, I might find one partway through. It really depends on how sparse or dense the graph is. This one is a hard one because it really depends on how dense or how sparse it is. We could say O of V, really meaning I'll put a comment there, V divided by 2. I might find it about halfway through, but this really depends on how many entries there are in this row. Okay, for the adjacency list, as someone pointed out, the adjacency list is going to come out the winner here because we just want to know, are there any flights? Well, I get to the linked list for DFW and I say, is this an empty linked list? No? Well, then there's flights. So best case is O of 1. Worst case is O of 1 because I just check the linked list. Is the linked list empty or not? I know in O of 1 time. Average, well, if the best and worst are the same, then the average has to be the same as them. So, yep, that was a pretty easy question given the adjacency list. We just need to know if the list is empty. Okay, now what if we change our data a bit? What if I had 2 values associated with every one of these? So each edge has now 2 values. One is a distance, one is a cost. And now I want to determine if I want to know the greatest distance for the least cost. Like, I want to get out of New York. I want to go as far as possible for the least amount of money, relatively speaking. And this is, again, a nonstop flight, just a direct connection. So I want to find the greatest distance for least cost. And like to put some values in here, for example, this one would be 3.8 if we're talking about like miles divided by dollars. So that would be 3.7, 1.8, 0.47 approximately. So think about this one for both the adjacency matrix and adjacency list. The matrix is a little bit harder to represent with the multiple values in it. It was easier to give an example of the list with this. And also, while you're thinking about this one, think about whether it's similar to one of the ones we did earlier. Okay, so it turns out in terms of complexity, this one's going to be really similar to something we did earlier. When we looked at trying to find the closest airport or the cheapest airport, we had to look through every possibility before we knew which one was best. So our complexities here for finding the best ratio is going to be the same. There's going to be a slightly different amount of work per thing that we look at because we've got to add the division in there, but the big O is still going to be the same. So for the best miles per dollar ratio would be the same complexities as finding the cheapest one. Now, what if we wanted to make a harder problem? What if we wanted to determine the best route, say these were dollars, and I want to get the lowest cost from X to Y, even if there's no direct flight? Like, can I fly, let's say, for instance, right here. I could fly from SFO to Boston 2704 directly, or I could take 1846 plus 867. It looks like, doing the math in my head there, it looks like the direct flight is very, very slightly cheaper, but we would have to compare them to know that. And maybe there's others that are a little bit different. Now, this is a harder problem, and we're not going to solve this one today. This one is what's referred to as the single source shortest path. And so we're going to have to come back to that one. And when we come back to this one, we'll explain what that means, what single source shortest path is. But it's a different problem when we have not just one edge, but possibly several edges added together. It's a different problem. We're going to need a different algorithm for it. So if we look at this problem just in general, before we get to the Dijkstra's algorithm, so if I had a depth first search, if I did a depth first search, meaning like we did it with either recursion or with a stack, a depth first search is only going to work on trees. In a general graph, I might find the wrong answer because of multiple paths, because I found a way to get there. It's the best I've got. If I do a breadth first search, it can work for an unweighted graph. So for example, when we did project 1, if we use a queue in project 1, we do a depth first search or breadth first search. if all edge weights are equal in terms of how many steps does it take me to get from here to there, then the breadth first search will find the shortest one if all weights are equal. So for the harder problem of a general graph where there might be cycles and there's different weights on each edge, then we need Dijkstra's algorithm. And we're going to come back to Dijkstra's algorithm later on. So here's just an example of how the depth first and breadth first proceed. And we already talked about this earlier when we did like the different things with trees. Now, when we have a graph, if we want to explore the edges to discover if a path exists, so I just want to know, is there a path from SFO to, say, JFK? So if my goal is just to find if the path exists, depth first search will work fine. It will find out if a path exists. It'll answer that question. And this is basically project one with a stack flag turned on. It's going to find if there's a path or not, it'll find it. Now, if we look at the overall algorithm, here's laid out. This is basically project one when we're doing it with a stack. So I start out, everything is unvisited. I mark the start as visited and I push the start to a stack. While the stack's not empty, I get the next possible location from the stack. I visit everything adjacent to it. It says every child, or we could say everything adjacent. We search everything adjacent to that candidate. If that potential other one is unvisited, we mark it as visited, we add it to the stack, and then we decide if that thing is our goal, we return. We just stop the whole algorithm and say it's a success. Checking if it's the goal when we put it in is better than checking if it's the goal when we take it out. Because I could say, hey, this thing where I am right now is adjacent to three other things. It's adjacent to the goal and something else and something else. Well, that third one comes off of the stack first, and maybe that one leads to the whole rest of the graph. Then I pop all the way back down to the second thing I added. Can't go anywhere from there because it's already been added. Then I pop the first thing, and I go, oh, look, the gold was sitting on this stack for a long time. So it's better, more efficient if we check when we put it on. If we check when we take it off, it'll still work and still give us a valid answer. It just might take longer than it needs to. Okay, so here's an example of drawing it out on a graph and looking at the what's going on. So we've got the unexplored vertices, visited vertices, ones that we basically have been added to the stack. Oops, I'm reading a question there. Oh gosh, James, it's been so long since I've been a math student and done transitive closure. Maybe. I'm going to give you a definite maybe on that question, James, because it's been so long since I've done a transitive closure. That might be a good one for like office hours. Find one of my IAs who's a math major. Talk to them. Or a math minor, maybe. Okay, so in this one, we've got the unexplored edges. We've got the visited vertices, are things that have been added to the stack. Unexplored edges we haven't finished looking at yet. So, and then discovery edges are the ones that we have taken off the stack. Now, back edge is a term that comes from CLRS. Back edge is basically saying it's an edge that I haven't explored, but if I did use this edge, it would go to somewhere that's already been marked as visited, and so we don't use it. So we start out in the bottom left. Down here is our starting point. I should have labeled our starting point. So we start out, we add A to the stack, we mark A as visited, then we take A off, And let's assume that we add to the stack in alphabetical order of adjacent vertices. So when A is there, we add B and C and D to the stack. Once we've added B, C, and D to the stack, then we can take off of the stack, we take D off of the stack. So this is really where we are right now. We're at D, and we're saying, hey, where can I go from D? Well, I could go back to A. A's already visited. I could go over to C. C's already visited, even though I've never looked at this edge. This edge doesn't help me. And then we go to the vertex C. Okay, so now when vertex C comes off of the stack, we would say, hey, I can take C off of the stack, and where can I reach from C? Well, A is already visited, D's already visited. Ooh, I could reach E from here. E gets added to the stack, and then we discover that E is the goal, and we stop because we've added the goal to the stack. B is still sitting on the stack also. It never got popped off because it was never one that we needed to consider to find the goal. Okay, so if we do this depth first search, we are going to, it's when we say called for each vertex, what we mean by called for each vertex here is each vertex is going to be pushed at most once. So there might be some vertices that never get pushed because they're a ways away and we find the goal before we ever reach those vertices. So every vertex will be added to the stack at most once. If it is added to the stack, it will be popped at most once. The ones that get popped, then we have to visit their adjacency list. So when I pop one off and I visit its adjacency list, it takes me 1 plus E divided by V time to visit everything that this vertex is adjacent to and see, hey, has this vertex already been visited? If not, push it to the stack, etc. So if we multiply those together, O of V times O of 1 plus E over V, we get O of V plus E. So the depth first search is linear in the number of vertices and edges. And this was, I forgot to mention this, it's in the title of the slide, we've been looking at this from an adjacency list perspective. Okay, what about if we did depth first search with an adjacency matrix this time? Okay, so still, we're going to visit each vertex at most once. So I visit every vertex at most once. Some I might never visit because I found the goal before I needed them. So I'm going to visit every vertex at most once. When a vertex comes off of the stack, we have to look at everything in its row to see who else is adjacent to it. And that would be O of V. That gives us O of V squared. So our complexity here looks like the adjacency list is the way to go because it's O of E plus V. It's linear instead of O of V squared, which is quadratic. It's not that the adjacency matrix is better or that the adjacency list is better. It depends on, is your graph dense or sparse? So remember, if we've got a sparse graph, E is proportional to V. In a dense graph, E is proportional to V squared. So let's look back. If we do the adjacency list, remember the adjacency list was O of E plus V, which could be with a sparse graph. That would be O of, well, E is proportional to V. V plus V, which is O of V. But if I did it with a dense graph, that would be, O of V squared plus V, which is equal to O of V squared. So if I use a list and the underlying graph was dense, I get the bad complexity just because it's a dense graph. Now let's say I did an adjacency matrix. Adjacency matrix doesn't depend upon the density, or how many entries. It doesn't depend on the density in terms of the complexity. If I do the O of V squared with the adjacency matrix, it doesn't matter whether the underlying graph was sparse or dense. I still have to look through everything in this row. Whether there's lots of infinities or no infinities in this row, or really one for the self edge, whether there's lots of infinite values or very few, I still have to look through all of them, and I'm going to end up with O of V squared either way. But in the list, it depends on whether it's dense or sparse. So it's not that using the adjacency list is a win. It's that if it's a sparse graph and you use the adjacency list, you get a better complexity. Okay, now let's look at breadth first search. Assuming there's no questions, there might be. We may be returning to that in just a minute. So in a breadth first search will always discover a shortest path if it's unweighted. If it's unweighted, breadth first is going to give us the shortest path. Well, it will give us a shortest path because there could be more than one. There could be, this route takes three connecting flights, that path takes 3 connecting flights, they both take 3 connecting flights. So I will find one of the shortest paths if all weights are equal. So like if it's, for instance, how many connecting flights did I have to have? All connecting flights, if we assume they have an equal cost of, hey, each connecting flight is 1 extra connection, and I don't like that. I'm trying to minimize my number of connections. Breadth first search would give us the shortest path. So it only gives us the shortest path, though, if it's an unweighted graph. If it's a weighted graph, we got to go to Dijkstra's, which we'll do in another lecture. And we're going to use a queue for this. The algorithm is basically the same. The only thing we've changed is to say push to a queue, pop from the front of the queue. Other than that, the algorithm is exactly the same. Thank you. That was my suspicion, was that it would be a inefficient but possible way to do it. I think when we do the Dijkstra's, it can't be any worse than transitive closure. It might be more efficient. Okay, so here's an example running through the breadth first search. And the breadth first search, I've labeled everyone with how far they are from the starting point. So L0, L1, L2 would be down below that. So we start out at vertex A, and we start adding the things to the queue that are at a distance of 1. So we add B to the queue, we add C to the queue, we add D to the queue, and those all go into the queue. So after this slide is done right now, our queue contains B, C, D. And let's assume that we're starting at A and we're trying to go to F. So we haven't stopped because we haven't found our goal yet. So then we go back through and we take B out. So now B is our current location. From B, I could go back to A, already visited. I could go from B to C. Well, that's an edge that doesn't help me because C's already been visited. I could go from B to E. So that's moving down here. So I could go from B to E. I add E to the queue. So right now my queue is C, D, E. Okay, so then we take C out of the queue. So now C is my current location. C is my current location, and we start searching from C. Well, from C I could go back to A, back to B. I could go over to D, which has already been visited. I could go to E, which has already been visited. Or, we got to go to the next slide to this, or I could go from C to F. So I could go from C to E, I could go from C to F. Aha! When I add F to my queue, I've found the goal, and we've located our goal state. Now, the complexity for this with the adjacency list is exactly the same complexity as the depth first search. For both the list and for the adjacency matrix, they're both the same complexity, whether we're doing breadth first or depth first. Now, Dijkstra's algorithm, like I said, we'll talk about this. We're going to have a whole lecture on this in the future, or half a lecture maybe. So we'll talk about Dijkstra's in the future. Dijkstra is going to find us the shortest path from the source S to the goal G. And like I said, we'll talk about that one later. And then we're basically at the end here. We've got all our background definitions, all that stuff we did, how we could implement and store a graph as an adjacency matrix or as an adjacency list, how we can do depth first and breadth first, when breadth first is best, and just a upcoming mention of Dijkstra's lecture, which we will have upcoming. And I've got the slides uploaded to Canvas for like the next 3 lectures, and I'll add more in the near future. Okay, so I'm going to leave the presentation going for a few minutes in case people have questions, and then I'll stop the presentation and we'll stay in the channel for a little bit longer, answer any remaining questions. So if anybody has a question that I need to go back to a previous slide to answer, now would be the time for that one. And of course, I have to wait for you because you're behind by about 30 seconds, I think. Excuse me. Yes. So when we did Project 1, and now I'm lost. It's been so long since Project 1, I can't remember which Project 1 we did. Because I've got so many different Project 1s. Okay, Puzzle Solver. So yes, so Puzzle Solver will find the shortest path when we do queue mode. And that's because we assume that we're counting the number of steps it takes. Like if we're talking list output mode, in fact, it will find the shortest list output mode. And yeah, and Project 1, yeah, Project 1 was equal lengths. If we assume that like each thing in list output mode is 1, they all count as 1, they all have equal cost. Okay, where can we find a proof that BFS yields the shortest? I think we could do that proof by contradiction. It might be in CLRS. I would take a look there and look at CLRS and breadth first search in a unweighted graph. There may be a proof in there. I don't remember. But if we think about it, Elang, assume that it didn't find one. Well, if it didn't find one, then at some point it would have visited a vertex that could have reached the goal, but didn't take that edge. But I can prove that it did take that edge. So your assumption must be false, and it must have taken that edge that would have reached it in the shortest path. That's a pretty hand-wavy proof by contradiction. But I would start with CLRS. And I think proof by contradiction is going to be the way to go. Yep, you're welcome. Thank you everyone for your patience, especially with our trolls, and we got through it. For the people that watch this video, they're not going to know what we're talking about because those are eliminated from the chat now, but we'll try to find a better solution for this in the future and see if we can maybe make it private to begin with. So thanks everyone. I'm going to end the live stream as soon as I can find the right window and the right way to do that.